Okay, welcome back. We want to discuss about units today, but to conclude the topic we discussed on in the previous video about the uh, ring of integers and the class group. One more thing we want to discuss that. So let's say an example in Zi, we have the fundamental discriminant is the discriminant of Zi, which is the ring of integer in Qi, and that is given by determinant of 1i, 1 minus I. So this is equal to square. So it is minus 4, right? The fundamental discriminant is minus 4. And minus 1 is congruent to 3 mod 4. So that matches that it should be like this. So you notice that minus 4, the Legendre symbol with respect to P is same as, of course, the Legendre symbol of minus 1 with respect to P. And this is equal to 0 if P is equal to 2, and it is equal to 1 if P is congruent to 1 mod 4, and it is equal to minus 1 if P is congruent to 3 mod 4. Okay. And we know that if P is congruent to, and we know that in Zi, which is O of minus 1, right? In O of minus 1, in our notation, for D is equal to minus 1. In this, we have that 2 times Zi. So we have this ideal 2 equal to 2 times O, 2 times this Zi. This ideal is equal to 1 plus I whole square as an ideal. And P equal to P times Zi is a prime ideal. So 3 cases. Prime ideal if P is equal to mod 4. And we have seen that P equal to P times Zi equal to A plus Pi to A minus Pi, and both A plus IB and A minus IB are prime ideals in Zi with A, B, and Z, and E squared plus B squared equal to P in this case. So here we can write in this last case P equal to if P is congruent to 1 mod 4. So P we can write equal to P1, P2. P is congruent to 1 mod 4, where Pi is the prime ideal. Okay, so you look at the fundamental discriminant, and the value of Legendre symbol of the fundamental discriminant tells you how, whether the 3 cases, the prime ideal, a prime below in Z becomes square of a prime. So this can be written as equal to P squared, where P equal to 1 plus I is a prime ideal in Z. So there are 3 cases. One is that, so as I said, there are 3 cases. And so the discriminant, the Legendre symbol of fundamental discriminant decides how an integer prime for an integer prime p in z p o x1 looks like. Okay, and in fact it looks like one of the three possibilities. It remains a prime ideal if the Legendre symbol of the discriminant is -1, right? If it is -1, then it is this case, right? So -1, this corresponds to this case, and so if we say that uh, 0, then 0 corresponds to this case, and p square is the prime ideal, and the last one is like this. So this corresponds to this case. Okay, so Legendre symbol determines how the prime in. So this can be generalized. This can be generalized to any quadratic Q. Q. Okay. So we'll not go into the precise detail, but so we studied for some time finite field, and with respect to that, we studied this quadratic reciprocity, and this is one of the application of the quadratic reciprocity. Fundamental discriminant of the quadratic, fundamental discriminant or the Legendre symbol of the fundamental discriminant determines how that prime behaves when you extend that prime. So the prime ideal p times OD may not remain a prime ideal. It will be an ideal in OD. It's a principal ideal in OD. And several cases can happen that it may remain a prime ideal, like Zi is the case. And that is besides the case if the quadratic residue is -1. It may become square of a prime ideal. It is precisely the case if the fundamental is 0, and last case is if the Legendre symbol is 0, and the last case is so actually this is not true, so be a bit precise. Yeah, because of the 4 factors, so this is equal to like, yeah, now it is precise. So so this quadratic reciprocity we can be used to describe how the prime ideals below in Z behaves in the prime ideal in trigonometry. So this is one thing which we will remember. Okay, so moving on to a next topic now, we want to study this units in the main theme today, that units in quadratic field we want to understand. Okay. So this is so we studied prime ideals in some sense and ideals, and so we basically understood how when it becomes a PID and not, and what is the failure. Failure is the ideal class group which measures this failure, and without proof we stated if it is a PID if and only it's UFD, and we saw some property that every prime ideal, the quadratic ring, non-zero prime ideal is maximal. Every ideal is then by at most 2 elements. It may be a PID, it may not be a PID. The class group in the imaginary quadratic field can be computed. It's a finite abelian group. We have proved it, and its size is the number of reduced binary quadratic forms, which are reduced positive definite and reduced positive definite binary quadratic forms, primitive, which are discriminant equal to the fundamental discriminant of the imaginary quadratic field. And we saw several examples of it. So that understanding more or less give us some understanding of ideals and prime ideals. And every ideal, again, without proof, we have stated, can be written as product of prime ideals uniquely. So that also is stated without proof, but the class group we understood in detail, at least with some imaginary quadratic. So now, as I said, the important things to understand is unit, another important thing. So that's what we will do. We want to understand what are the units in OD. Okay, so let D be a square free integer, and recall that the ring of integer OD we just discussed is Z root D, which is A plus B root D, where A, B are in Z, if D is 2 mod 4 or D is 3 mod 4. And it is Z 1 plus root D by 2, which means A plus B times uh, A plus B into 1 plus root D by 2, where A, B are in Z. This kind of this M plus A plus B times A 1 plus B times 1 plus root D by 2, where A, B both vary in Z freely, if D is congruent to 1 mod 4. So this is the ring of integer of the quadratic field, and under the usual addition and multiplication of complex numbers. So also we have seen this, and if a element A plus B root D is in Q root D, then we have this map sigma from Q root D to Q root D, which is the field isomorphism. It takes A plus B root D to A minus B root D, and we denote it by A plus B root D bar. D may be even positive, but this is just a notation. So this is like definition. And in case D is real, this is really the D is imaginary. So D is less than 0. In case D is less than 0, then this is really complex conjugation. Otherwise, it's not. But we nonetheless denote it like this. And the norm of A plus B root D is A plus B root D into A plus B root D bar, which is A square minus B square D. And we know that this property holds that norm of xy is equal to norm of x into norm of y. Okay, for all xy in O Q root D. An element x in a commutative ring we call is a unit. So what is a unit? If there is, it has an inverse, multiplicity inverse. If there is another y in A, so that x times y equal to 1. So A is a commutative ring with 1, and some element is an unit. If it is a multiplicative inverse, of course, we have seen this. And the set of units is denoted by A star usually. This is the notation we have used. For example, the units in Z are only plus 1 and minus 1. For no other integer m, 1 by m belongs to Z unless Z, m equal to 1 or minus 1. On the other hand, for field, every non-zero element is an inverse. So for field, the group of units is just f minus 0. Okay. So we want to focus, as I said, we want to understand what are the units in OD, where so we want to understand what are the units in OD, where D is square free. So x be a unit in OD, that then there is to y such that xy equal to 1 and it's commutative. So then norm of xy is norm of x times norm of y, right? So so it is 1. And since x belongs to z, norm x is the coefficient of the minimal polynomial. So x satisfies x squared minus trace. So x belongs to OD plus x squared minus trace of x into. Okay, so let's use the notation alpha. Alpha belongs to alpha square minus trace of alpha into x plus norm of alpha equal to 0, and this is belongs to so f of x equal to x square minus trace x into alpha. This belongs to zx, and f of alpha equal to c. So this is the minimal polynomial of alpha unless alpha is already in z, right? This is so this is okay. So this is the minimal polynomial. So trace and norm are in z, and so norm of x into norm of y are in 1, and norm x and norm y in z. So product of two integers is 1. So both of them has to be equal, either plus 1 or minus 1. So norm x belongs to plus or minus 1. Also, x belongs to OD implies sigma x is also in OD. So because sigma x will also satisfy the same polynomial, right? So f of sigma alpha is also equal to 0. You can only alpha, right? So sigma x also belongs to a OD, so that means norm of x is plus 1 or minus 1. So x is in OD star. So what we obtain that x is a unit if and only if norm x is plus 1 or minus 1. Okay. So explicitly, so norm x is plus minus 1 if and only if x is in OD star, right? So we can do this more explicitly also if you like in this case. So this is a criteria. An element is a unit if and only if norm x is plus minus 1. So we set out to find all the units. So I'm saying we set out to find all the elements which are norm x is basically plus 1 or minus 1. So to find all the units, it suffices to find all norm 1 elements. Okay. So this is the criteria, useful criteria which we want to use. That something is a unit if and only if it has norm. In the ring of integer of a quadratic field, something is a unit if and only if it is norm 1. Okay. So we can do this more explicitly. So let's say d is equal to 2 or 3 mod 4. Then x, an element has norm 1. If AB belongs to Z, then sigma x equal to a minus b root d, and norm x is a square minus b squared d. And if d is congruent to 1 mod 4, then x is equal to, can be written as, so norm x looks like this. So from there you can deduce that x is in OD if and only if norm x is plus minus 1. Or if d is 1 mod 4, then sigma x is a plus b into 1 plus root d by 2. That means sigma x is a plus b. You can write the same thing as a plus b minus b into 1 plus root d by 2, right? So norm x is nothing but a square plus ab plus b square into 1 minus b by 2. This is a small calculation. So what will happen? Yeah, so you just take product of these two, then you easily calculate this. And since d is 1 mod 4, d square minus 1 divisible by 4. So d minus 1 by 4, this is in z. So that's how you can explicitly calculate the norm. And again, you can arrive at this thing. Okay. So in summary, an element, this is important, is a unit in the ring of integer of a quadratic field. If and only if following happens, the norm x is in unit in z, and so norm x is plus minus 1. Okay, so an element is in, so this is what I said, that an element is a unit in the ring of integer of a quadratic field, if and only if its norm is plus 1 or minus 1. So we can directly write this, we don't gain anything by writing this. So okay, so OD is z root d if d is 2 or 3 mod 4, and it is z1 plus root d by 2 if d is 1 mod 4. Okay, so anyway, so let us now, so now we want to calculate all norm 1 or norm minus 1 elements. Okay, so we have to calculate all them. So the easy case is, d less than 0. Okay? Maybe I will put it here. So the easy case is when d is less than 0. So let us deal with that. So first assume d is less than 0, then OD star is set of elements such that norm x is plus minus 1. But so let's again, among that, let's take d is equal to 2 or 3 mod 4. Okay. Either 2 or 3 mod 4. Then x is a unit. So x looks like a plus b root d. So x is a unit if and only if a square minus b squared d is plus minus 1, right? That is the norm. So the norm is plus minus 1, a, b are in z. That means, but d is negative, right? D is less than 0. So minus d is positive. So a is an integer, b is an integer. This cannot take minus 1. So that means a square minus b squared d must be equal to plus 1. So now again, this is an integer, a square is a positive integer. and minus b squared d is also a positive integer. So, and their sum is equal to 1. So both the integer must be, a square must be also less equal to 1. Sum of two positive thing is equal to 1, and minus b squared d, right? Minus b squared d, that also must be less equal to 1. Now, if minus d is, so now you look at this one, this guy first. Minus b squared d is less equal to 1. So if d is already minus d, if minus d is greater than 1, okay, minus d is 2 or 3 or whatever, then this the b square is an integer. So this can never be less equal to 1. So then only possibility is b is equal to 0. Okay. So if b is equal to 0 and a square is less equal to 1, that means a could be equal to plus minus 1. So d star, the only units are plus 1 and minus 1. So after all this theory, we got the two units are plus minus 1. Okay. So since, yeah. So since anyway, since, so even before saying this, one thing to note that since Z is a subset of OD, or subring of OD, subring, right? So this implies that plus minus 1 is always inside OD star, right? It's a subgroup of OD. Plus minus 1, these two units are always because they're already units in Z. And Z is included inside this, right? Z is sitting inside OD. Okay, so that means plus minus 1 is always there. So here we are reduced to case plus minus 1. Okay. So if d is minus 1, so we are doing two or three mod cases. So if d is minus d is greater than 1, then b is equal to 0. And we get only two units plus 1 or minus 1 because a is an integer. If minus d is equal to 1, that is also possible. Then you get b, then b square is less equal to 1. So it's possible that b is plus 1 or minus 1. Okay, so b square is 1. If b square is 1 and d minus d is 1, so then you get a 1 plus a square is 1. So a square is 0. Okay, so a square equal to 0. So on the other hand, if a square is equal to plus minus 1, then a square plus b square is 1. That means b has to be equal to 0. So the possibilities is a either a equal to 0 and b is plus minus 1, or so this is minus d equal to 1. So d is minus 1, right? So what we are talking about, d is minus 1 meaning we are talking about z iota. We are talking about q square root of minus 1, right? That's what this corresponds to. So q root of minus 1, so the ring of integer is zi, right? So o minus 1 is nothing but zi. So we are talking about union of zi, and indeed you know that plus minus 1 and iota is itself a unit because it's fourth root of unit, right? So it is plus minus iota. Okay, so the units here are plus minus 1, plus minus iota, and we did this computation right here. So if b is plus minus 1, that means you get a plus bi, right? The units were a plus b root I minus 1, so a plus bi, so you get plus minus I. So either the units are plus minus I or units are plus minus 1, right? The b equal to plus minus 1 and a equal to 0 means the element was a plus b into root of d. So d is minus 1 and b is plus minus 1 and a is 0. So it is 0 plus minus iota. So plus minus iota. So this is these two elements. Or if b is 0, then you get a equal to plus minus 1. So plus minus 1. So these are the four possibilities. This group is also, by the way, this group is cyclic, right? This is isomorphic to Z mod 2Z. Here also, although it has four elements, this is actually isomorphic to Z mod 4Z and presented by, for example, I. Okay, so, or minus I, whatever. Now look at the other case. We are still assuming that d is less than 0, and if d is 1 mod 4, so then x equal to a plus b into 1 plus every element looks like this. So it belongs to O D star and A, B are in Z. Typical element looks like this, right? So if this is a unit, then its norm is 1. And what is the norm? Norm is a plus b by 2 whole square, and its bar will be a plus b into 1 minus root d by 2, right? We have calculated a plus b minus b into 1 plus root d by 2, right? This was the norm. So so this was the x bar, if x was this, which is also a plus b So we have written it in this way here, a plus b, but it will be a plus b into 1 plus 1 minus root d by 2, which can be also be written as a plus b minus b into 1 plus root d by 2. So either way, its norm you can calculate. The norm is a plus b by 2 whole square minus b squared d by 4. Right? This will be the norm. Okay? You can calculate here also. It is a plus b by 2. So this one you can write it as a plus b by 2 square minus b square b. This is the norm. Okay? Yeah. So this has to be equal to plus minus 1. But here again, minus d is positive, so everything is positive. So it cannot be minus 1, right? Because minus d is positive, and this is a positive square, so it's a positive integer, it's a positive number. So sum of two positive number cannot be negative, so this has to be equal to 1. So again, this is a positive number, and minus b square by d is positive number. So x square plus y square is 1, x square is real number. That means x square has to be less than 1 and y square has to be less than 1. So b square times minus d has to be less than 4, and a plus b by 2 whole square has to be less than equal to 1, right? So this person has to be less than equal to 1. And this person also has to be less than equal to 1. So, and we are in the situation d is 1 mod 4. Remember, we are in this situation d is 1 mod 4. So, and d is 1 mod 4 implies minus d. So, let us look at minus d. The minus d is positive. Minus d is 3 mod 4. So, if minus d is greater than 3, so minus d can be like 7 or something. So, if minus d is greater than 3, then this is, and it is 3 mod 4. So, next this has to be like 7, right? So minus d can be 7. So then this will be more than 4. So that's not possible. So b has to be equal to 0. B is an integer, so b has to be equal to 0. B square has to be 0, so b is equal to 0. So once you get b is equal to 0, you come back to this equation, right? This one vanishes, so a square equal to 1. That means a belongs to plus minus 1. A equal to plus minus 1 and b equal to 0. So you go back to this here. So the element is x equal to then a, and a takes value plus minus 1. Anyway, plus minus 1 is there. So you got very simple thing that minus d, if it is greater than 3, strictly greater than 3, then we get OD star has to be equal to plus minus 1. Next option for minus d is only 3. Well, minus d is 3 mod 4, so it cannot be 1 or 2. So you have to check only one case, minus d equal to 3. So minus d equal to 3 refers to which case? So you are inside q square root of minus 3. And what is the ring of integer? Here O minus 3 is Z 1 plus root minus 3 by 2. Okay, so this is the cube. This is also q omega. This is also same as q omega, and omega q is equal to 1. So this corresponds to, I'll just say, this corresponds to d equal to minus 3. This corresponds to q root minus 3. Okay. So if minus d is 3 anyway, you put minus d equal to 3, then you get 3b square is less than equal to 4. So the value of b can be 0 or value of b can be 1 or minus 1. If value of b is 0, you again get, you look at this element. If value of b is 0, then you get plus minus 1. Okay. But so a belongs to plus minus 1, and this is your unit. If b can be plus 1 or minus 1, so then what is the equation? Norm equation here, you look at this norm x, a square plus ab, and you have put minus d equal to 3. So this is a square plus ab plus b square. This is the equation. And b square is 1, and b can be plus 1 or minus 1, right? This is the equation. A square plus ab plus b square into 1 minus d by 4. And what is minus d? Minus d is 3. So it's 3 plus 1, 4 by 4. So this is 1. So a square plus ab plus b square. And b can be, b square is 1. So this is a square plus ab plus 1. And b can be plus 1 or minus 1. So either it's a square plus a plus 1 or a square minus a plus 1. Right? So b equal to plus minus 1 implies a square plus a plus 1 is 0 or a square minus a plus 1 is 0. So a square plus a plus 1 means it's the cube root of unity, right? Omega. So omega, you put omega equal to minus 1 plus root minus 3 by 2. Then this is the root of a square plus a plus 1. Then this one is 1 plus omega. 1 plus minus root 3 by 2 can be written as 1 plus omega. But you know 1 plus omega is minus omega squared. So there is this identity. So ultimately you get 6 roots of unity. This will give you omega, then you will have omega squared, and then you have minus omega, and then you have minus omega squared. Okay, so and plus minus 1 is there. So there are 6 roots of unity. You can check. So what we have proven for an imaginary quadratic field, the classification is very simple. If d is less than 0, then OD star is plus minus 1, unless d is minus 1 or d is minus 3. In case of minus 1, O minus 1 star is Z iota star, it is plus minus 1 plus minus I, and is a cyclic group generated by I, Z mod 4Z, and O minus 3 star is Z omega star, where omega is minus 1 plus root minus 3 by 2, omega cube is 1, so omega satisfies this equation x squared plus x plus 1, and in that case, the roots of unity are plus minus 1, plus minus omega, and plus minus omega squared. This group, by the way, is isomorphic to Z mod 6Z, and this group is isomorphic to Z mod 4Z, and this is isomorphic to Z mod 3Z. So there are 3 options: cyclic group of order 2, cyclic group of order 4, cyclic group of order 6. This is generated by minus 1, this is generated by omega, this is generated by iota, for example. Okay, so and that's specific only for Z minus 3. There is a different answer. Q root minus 3, there is a different answer, and Q root minus 1. So once you dispose the easy case, now you move into the case where D is positive. Okay, so now assume D is positive and D belongs to Z, square free, and D belongs to Z, square free. So in fact, it's 1. And then if D is 2 or 3 mod 4, then again it is the norm, if norm x is equal to plus minus 1. Now in the real case, so again you write x equal to a plus b root d, a belongs to z. Then a plus b root d is a unit. That means it's an OD star, if and only a square minus b squared is plus minus 1, and both can happen. And if in this case, if no, we have already assumed b square free, so let's say maybe right here. Also, d greater than 1 square free integer. If this is the case 1, first case, if that's the first case, if d is 2 mod 3, then we will show that the sum of the Pell's equation has infinitely many solutions in Z. So this is we will show. Okay, so we'll only focus on plus 1, and we'll show there are infinitely many solutions. That means there are infinitely many units with norm equal to 1. Okay, and even and 2 in the second case, excuse me. Moreover, 2 moreover if d equal to 1 mod 4, So then writing this, we'll see that z root d will be contained inside this. See then, so contrast this with the, so imagine a quadratic field, we saw there are always uh, finitely many units. In fact, other than two specific cases, there are only 2 units. Other cases, there are 4 or 6. So there are at most 6 units. In this case, we'll show that this equation x square minus y square d equal to 1. This is called Brahma-Gupta-Bell's equation. This is a famous equation. Actually, uh, kind of it is incorrectly attributed to Pell, and I mean it was discovered by someone else, but Pell has very little to do with this equation, and it was certainly discovered by Brahmagupta, who was the ancient Indian mathematician, and so he discovered that it's an infinitely many solution. So if xy belongs to z, then we'll show that there is infinitely many a plus b root d in OD star with norm equal to 1. So that means this equation has infinitely many solutions. So that means you get infinitely many a. So you can write then, so you get corresponding to that xy, you take x plus y root d, then that gives you infinitely many units, which has like, okay, so this can be written as what I'm saying. So this can be written as x plus y root d into x minus y root d. So then infinitely many xy gives rise to infinitely many x plus y root d, and all of which is norm 1. So you get equal to, so you get equal to infinitely many units. So equal to norm of plus y root d. Um, so you get infinitely many solutions. So there are infinitely many units compared to the real quadratic. Now you will say that, okay, if d is 1 mod 4, then the ring of integers is not z root d, but it is contained inside z1 plus root d by 2, right? Because every element a plus b root d, I can rewrite as a minus b plus 2b into 1 plus b root d, right? So it is 1 into a minus b plus 2b into 1 plus root d by 2. So it belongs to, so this element belongs to z1 plus root d by 2. So z root d is contained inside this thing. And this is a subring, so any unit here is a unit here. So if xy satisfies that norm of x plus y root d is x square minus dy square for integers x and y, then so then you get, so from infinitely many solution, if you can show this as infinitely many solution again using Brahma-Gupta-Bell equation. So basically we'll only study x square minus dy square equal to 1 as infinitely many solutions. So for d equal to 2 more or 3 more 4 case, that straight away gives you infinitely many elements with norm 1. Infinitely many elements with norm 1, so there are infinitely many units with norm 1. In the case of 1 plus root d by 2, you get that even in case of that, it contains z root d. So if you can show in this case also for any d, x square minus dy square 1 has infinitely many solutions. So then again, you get infinitely many norm 1 element inside z1 plus root d by 2. In fact, you can see this in another way. If norm of x plus root dy is equal to 1 and d is, let's say, 1 mod 4, then x minus y 2y satisfies norm of this is equal to 1, right? This is x minus y plus 2y into 1 plus root d is nothing but x plus y root d. And this element is is an element in, as you can see, this is an element in 1 plus root d by 2, and xy going to x minus y and 2y is injective. So for infinitely many integer solution of this, we get infinitely many units in OD for any d greater than, right? So this case, 1 mod d case, we'll find infinitely many solution x square minus dy square equal to 1. And because this ring is a subring of this, units here will give you infinitely many units here. And I'm saying the same thing in another way. It's repeating the same thing twice, that if x, norm of x plus root dy is 1, then x minus y 2y is an element here which satisfies this norm 1, and infinite limit xy gives rise to infinite limit xy here. So this way also you can see that this will have infinite limit. So as far as we are concerned about infinite limit units, it suffices to show for whichever be the case that d greater than 1, both d equal to 2 mod 4. So both d equal to 2, 3 mod 4 and d equal to 1 mod 4 case. So for both cases, it suffices to show, if I show that x square minus dy square equal to 1 has infinitely many solution, then you get infinitely many units in OD. Okay, so that's the goal. So focus now on studying this. So let's see an example before we go into the theory. So for example, d equal to 2, then ring of integer is z root 2 and z root 2 star, the units in z root 2. Actually, one can check that it is of the form. So we'll tell you something about it later. How to find this root 2 plus 1 to the power n in z. So all the units are the power of root 2 plus 1 to the power n. Okay, so this is isomorphic to plus minus 1 and 1 plus root to the power n in z. So 1 plus root 2 is of norm 1 and its square is also of norm 1 and any power, its inverse is also of norm 1. So, so because a square minus 2b square equal to 1 implies a plus b root 2 into a minus b root 2 equal to 1 implies that norm of a plus b root 2 equal to 1. And if you take u equal to 1 plus root 2, the norm of u is minus 1. So norm of u square equal to 1. And u square is what? 1 plus root 2 square is 3 plus 2. So if I look at, so earlier we said we'll focus on this x square minus 2y square equal to 1. And you can show that all elements here looks like 3 plus 2 root 2 to the power n, where n is in z. So 3 plus 2 root 2 satisfies this. So we'll say a little bit more about this in a while. Why I'm talking about power, I'll explain in a bit. So in this case, all the units are given by like this. This is a complete solution. So plus minus 1 is always a unit. And other than that, so notice this root 2 plus 1 is greater than 1. If root 2 plus 1 is greater than 1, then root 2 plus 1 to the power n, these will be distinct numbers. So these are all distinct numbers, okay? And why root 2 plus 1 to the power n we are considering, I'll tell you in a while. But look at another example. Let's say d equal to 5. Then we know the ring of integer is 1 plus root 5 by 2. And you just look at this element 1 plus root 5 by 2 into 1 minus root 5 by 2. Then what is it? This is minus 1. So that means that 1 plus, so this implies, so you define alpha to be 1 plus root 5 by 2. Note that this doesn't belong to z root 5. Okay, so this is an element which is in z 1 plus root 5 by 2, but it's not in z root 5, and norm of alpha equal to minus 1. Okay, so this implies that alpha is in O5 star, the unit. Okay. Now we define beta to be equal to alpha cube, 1 plus root 5 by 2 to the power cube. Then denominator you have 8, and numerator you have 1 plus 5 root 5 plus 3 into root 5 square. So 15 plus 3 root 5. This is 2 plus root 5. This belongs to z. And so here, for example, here, so you look at 2 plus root 5, right? So 2 plus root 5 is 2 plus 1 into root 5, right? So x plus y into root 5. And this 2 comma 1 satisfies x square minus 5y square. Now you define delta to be equal to beta square, 9 plus 4 root 5, right? What is 2 plus root 5 square? It's 4 plus 5 plus 2 4 root 5. So 9 plus 4 root 5, this is in z root 5. And this 9 plus 4, and this tuple 9, 4, this satisfies x square minus 5y square. Okay, so see, so there are more units in this ring than in z root 5. But later we'll introduce this concept of, this is the sort of the fundamental unit here. Like here, for norm 1, the fundamental unit is 3 plus 2 root 2. We'll say what is fundamental unit and what is the relation. We'll discuss in a while. But this fundamental equation unit satisfies x square minus 5y square equal to 1. So some finite power of this is here. Okay. And more generally, this so finite power of this unit in Z root 5 in O5 is in Z root 5 inside the smaller subunit, right? So and we can even take norm one element. So what I'm saying in some sense, norm one element already gives you a lot of information. Okay, so I want to say something. Maybe I'll continue. It's a good time to end this talk today, and we'll continue next time.